So good afternoon, everyone. So this will be the third session for the electrostatics, right? We'll be starting with the electrostatics part three for NEET 2024, right? So some of the important questions as well as PYQs will be discussed along with the concepts of all those questions, right? So we'll be starting with the question number one. The question number one says that a particle of mass m and negative charge q is thrown in a gravity-free space with speed u from the point A on the large charged sheet of uniform surface charge density, right? As shown in the figure. So we have to find the maximum distance from A on sheet where the particle can strike, right? So this is the infinite, or this is the large sheet, charged sheet, positively charged sheet, having the charge density. Let's suppose charge density is plus sigma, right? So plus sigma is the charge density of this infinite large sheet, right? We're projecting a negative charge of charge minus q and mass m, right, along this direction at an angle of theta with respect to this sheet, right? At an angle of theta with respect to the sheet. There will be electrostatic force on this charge minus q because of this electric field because of the sheet. We know that electric field because of the sheet is nothing. It is sigma upon 2 epsilon naught because of this non-conducting sheet, right? Now, there will be electrostatic force on this charge minus q. It has to be along this direction, right? This will be the force acting on this charge q because of the electric field here. That too because of the infinite charged sheet, right? Now you can see here this there is a constant force at an angle of theta with respect to the initial velocity u, right? Then this particle or this charged mass is actually going to follow a path, that's the parabolic path, right? So this will be the path of this charged particle, right? So it will somewhere strike here, right? Somewhere strike here, right? We have to find the maximum distance from A on sheet where the particle can strike, right? We have to find the maximum distance on A where the particle can strike, right? So the particle can actually, we know that it will follow parabolic path, right? Same as that of when we project a particle at an angle of theta, right? On the surface of the ground, it follows a parabolic path at an angle of theta, right? And the only force acting on this particle is the force due to gravity, that's mg downwards. And we know that the range or the maximum horizontal distance for this particle projected at an angle of theta, that's nothing. It's u square sine 2 theta over g, right? Sine 2 theta over g, where g is the acceleration, right? Or we can write here a range of this particle will be u square sine of 2 theta over the acceleration a, right? Acceleration a. Now, the work that is done by the gravitational force here and the same work is done by the electrostatic force here, right? So the purpose of gravitational force here is same as that of the electrostatic force here in this case. So it means that only the only the nature of the acceleration will change, right? Here the acceleration is because of the gravitational force, here the acceleration will be because of the electrostatic force, right? So the acceleration of this particle in the downward or towards this sheet will be nothing. It will be the force because of the sheet, that will be charge multiplied with the electric field to the sheet upon the mass m, right? So this will be the acceleration of this particle, right? Now the charge is q and the electric field is here is sigma upon 2 epsilon naught, right, upon m. So the net acceleration for this particle will be in this direction, that will be q sigma upon 2 m epsilon naught. So this will be the net acceleration of this particle, right? So this acceleration will be actually responsible for this parabolic path of this uh, particle, charged particle of mass m, right? So once again, the range of this particle will be u square sine 2 theta over the acceleration, right? Now the acceleration here is nothing. It's the acceleration because of this electrostatic force. We can replace this acceleration with q sigma upon 2 m epsilon naught. That will be multiplied here, right, in the numerator. So the net force here will be 2 m epsilon naught, right? U square sine 2 theta over g, right? Over g. Sine 2 theta over q sigma, right? Not g. Now here, if we find the maximum range or the maximum horizontal distance it can have, if we project this projectile, if we project this charged particle at an angle of theta equal to 45 degree, then only the distance will be the maximum here for this charged particle, right? So for theta equal to 45 degree, the maximum range or maximum horizontal distance will be r max. That will be 2m epsilon naught, right? U square upon q times sigma, right? So this will be the maximum horizontal distance that will be followed by this charged particle on this sheet, right? Let's move on to the question number second, right? The question number second is a simple pendulum of length L and bob of mass m is hanging in front of a large non-conducting sheet of surface charge density sigma. Let's suppose the plus sigma is the surface charge density of this infinite non-conducting sheet, right? If suddenly a charge plus q is given to bob, there's a plus q charge given to this bob, right, of length L, pendulum of length L in the position shown in figure. Find the maximum angle through which the string is deflected from vertical. So we have to find the maximum angle through which it will be deflected with respect to the vertical position of this bob, right? Now, why it will deflect? Because of the electrostatic field, because of this infinite sheet, right? And the electrostatic field, because of this infinite sheet, is sigma upon 2 epsilon naught, and it's along this direction. It means the force experienced by this charged particle q will be along this direction. That will be charge multiplied with electric field. The charge is q and the electric field is sigma upon 2 epsilon naught. So this will be the force experienced by this bob, right? So when this force acts on this bob, the bob will deflect, right? It will deflect, right? So let's suppose after some deflection, there will be some maximum deflection for this bob theta. And at this maximum deflection point, the net force acting on the bob will be zero, or we can say it will be a point of equilibrium, right? At maximum deflection, the bob will be at equilibrium, and the forces acting on this bob will be one force will be the because of the mass of this bob, right? It will be vertically downwards, right? It will be vertically downwards. That will be mg. That's the gravitational force, right? And this obvious force is the electrostatic force, that's q sigma upon 2 epsilon naught, right? And the string will be taut here. There will be tension because of the string, right? This is the tension T, right? This is the tension T. Now we have to find the equilibrium condition for this bob at this position where the theta is the maximum, right? Theta has the maximum value. Now you can see here, if we resolve the tension into two components, right? One component will be along this direction and the component will be along this direction, right? So if this is theta, then this angle has to be a theta here. It means this component will be t cos component, right? T cos theta, and this component here will be t sin theta. The vertical component will be the cos component, and the horizontal component will be the uh, sine component. Now, if we draw the free body diagram for this bob, mg will be along this direction, and there is electrostatic force, that's q sigma upon 2 epsilon naught along this direction, right? And there is one component of the force, that's t cos theta along vertical direction, and t sin theta component along horizontal direction, right? So now, since this is at equilibrium, this bob is at equilibrium, so all the force must vanish, or the net force on this bob at this position has to be zero. This is only possible when all the vertical forces sum to zero and all the horizontal forces sum to zero, right? Or we can say that t sin theta component must be balanced by this q sigma upon 2 epsilon naught, right? Or t cos component, t cos theta will be must be balanced by this weight mg of this bob, right? Now let's divide both these equations, right? So we'll be left with t and t will get cancelled. Sin theta over cos theta, it will be tan of theta, right? So it will be q sigma upon 2 epsilon naught m into g, right? So this will be the tan of theta, right? So the maximum angle theta here will be tan inverse of q sigma, right? Q sigma over 2mg epsilon naught, right? So this is the maximum deflection with respect to the vertical that this bob will have because of the electrostatic force acting on it, right? So this is how we can solve this question, right? With respect to the maximum deflection for this bob, right? Now let's move on to the question number three. The question number three says that two thin conducting shells of radius r and 3r are shown in figure, right? The outer shell carries a charge plus q and the inner shell is neutral, right? There is no charge on the inner shell, but the outer shell carries a charge of plus q, right? The inner shell is earthed with the help of switch S, right? There's a earthing for this inner shell, right? With the help of this switch S. Find the charge attained by the inner shell when switch S is closed, right? When we close this switch S, we have to find the charge on the inner shell, right? Now you can see here. So the this earthing done for the inner shell, it means that the inner shell will always be at a zero potential, or the potential of at the surface of this inner shell will be zero, right? And let's suppose because of this earthing, this shell attains some charge, and let's suppose q dash is the charge attained by this inner shell, right? And the total potential because of all the charge on this inner shell has to be zero because it's grounded, right? It's grounded, right? So then let's suppose q dash is the potential, right? So the q dash is the charge on this attained by this inner shell. So the potential because of this q dash will be kq dash upon r, right? And there will be a potential because of this outer shell as well, having the charge of plus q. The potential because of the outer shell will be plus kq upon 3r, right? And the total potential has to be zero because it's grounded, right? Inner shell is grounded. From here k and k will get cancelled, r and r will get cancelled, will be left with q dash will be equal to minus q upon 3. So this will be the net charge attained by this inner shell, or we can say this amount of charge will be supplied by the ground to this inner shell, right? This amount of charge will be supplied by the ground to this inner shell, right? And it will be a very instantaneous supply of this minus q upon 3 amount of charge, right? So the net charge, finally the net charge that will be there on this inner shell, that will be minus q upon 3, right? So this is how we'll do this question, right? Now moving on to the next question. The next question says that three large parallel plates have uniform surface charge densities, right? As shown, first plate has sigma, another plate has minus 2 sigma, and the third plate has the minus sigma as the charge density, right? Where to find the electric field's intensity at point P? At point P, we have to find the electrostatic electric field intensity, right? Now you can see here there are three plates of different charge densities, right? So the electric field at point P will be because of the electric field of all the three plates here, right? Now this is a positively charged plate, right? Positively charged plate. The electric field because of this positive charge at this point P will be along this direction. It will be along the downward direction, or we can say it will be along negative z direction, or minus k cap will be the unit vector for this electric field, right? And similarly for minus 2 sigma, the field has to be towards the negative plate, right? It will be along this direction. For minus sigma, it will be once again along this direction. It means the net field will be the sum of all the three fields, and they are parallel to each other. So we'll just algebraically add all the three fields to calculate the net field, right? So because of the first plate, it has to be sigma upon 2 epsilon naught, and because of the second plate, it will be 2 sigma upon 2 epsilon naught, and because of the third plate, it will be sigma upon 2 epsilon naught, right? So this 2 and 2 will get cancelled. I'll be left with it will be 2 sigma upon epsilon naught will be the net field, net electrostatic field, right? Now if we write this in the vector form, right? In the vector form, right? E net vector, since net direction of this electric field will be along downward direction, or it will be along minus k cap direction, right? Minus k cap direction. So this is the net electrostatic field, net electric field, because of all the three plates here having the charge density sigma, minus 2 sigma, and minus sigma, right? Now moving to the question number 5 here, right? The question number 5 says that for the situation shown in the figure below, we have to find the potential due to induced charge, right? We have to find the potential because of the induced charge. There is a conductor, hollow neutral conductor, right? In front of this conductor, we have placed a charge Q at a distance of t from this point P. The conductor, hollow conductor, is having a radius r, right? The hollow conductor is having a radius r, right? So the on the surface of this charged uncharged conductor, right? There will be some induced negative charge, right? Induced negative charge on this conductor, and some part of this conductor will have a positive charge, right? Because this conductor is electrically neutral before, it has to be electrically neutral after as well. So the amount of negative charge induced will be equal to the amount of positive charge induced, right? So the total charge on this conductor will be 0. But the charge density at different points for this conductor has to be different, because the induced charge here is because of this charge, external charge Q. So electric field strength will be more here. It means the more negative charge will be concentrated at this point. So the charge density at point P will be more than rest of the points. So we can say the charge here will be non-uniformly distributed. There will be no uniform distribution of this negative and or positive charge, right? Negative or positive charge. So what we can do here is that let's suppose this is the conductor of radius r, right? Conductor of radius r. So what we can do is that this is a radius of conductor of radius r. We have to find the potential because of the induced charge, right? There will be some potential because of this charge q, and there will be some potential because of this what we call as because of the uh, because of the induced charge as well, right? Now, talking about the center of the sphere, whatever be the potential at the center of the sphere, same has to be this potential at the surface of the sphere, right? Because we know inside the sphere, if there is no charge placed, if there is no charge placed inside the hollow sphere, right? Hollow shell, whatever be the potential at the surface has to be the potential inside this conductor, right? Now, the inside this conductor, the potential will be only because of the outside charge q, because for potential because of this induced charge at the center of this conductor has to be equal to zero, right? It has to be equal to zero. So at center potential, uh, at center, or we can say BC here will be the potential because of this charge q. It will be kq upon t plus r. This will be the potential at the center, right? This will be the potential at the center, and same should be the potential at the surface, right? This much will be the potential at the surface. That it means VC has to be equal to Vs, right? Now the total potential on the surface will be the potential because of the charge q, that is kq over t, and the potential because of this induced charge, right? That will be the potential on the surface, and that will be equal to kq upon t plus r, right? That will be equal to kq upon d plus r. So the potential because of the induced charge on the surface will be kq upon t plus r minus kq upon d, right? Kq upon d, that has to be equal to kq will be taken as common. It will be d minus t minus r upon t multiplied by t plus r, right? So from here t and minus t will get cancelled. We'll be left with the potential because of the induced charge here, that will be minus kq multiplied by r upon t multiplied by t plus r. So this is the net potential on the surface because of the induced charge, right? So this much of potential will be there because of the induced charge, right? Now moving on to the question number 6, right? Moving on to the question number 6, right? There are four charges are placed each at a distance a from origin. We have to find the net dipole moment because of the given configuration of the charges, right? You can see here each of the charges are placed at a distance of a from this origin, right? This is the origin of the Cartesian system, right? This charge is also placed at a distance of a. This is also placed at a distance of a, and this charge is also placed at a distance of a, right? The net dipole moment because of any discrete charge distribution is nothing. It's summation of qi ri vector, right? Where ri vector is nothing. It's the position vector of the AF charge, right? It's the position vector of a charge, we can say, right? So summation of qi ri, q is the magnitude of the charge, and r is the position vector of the given charge, right? So here for this charge, the position vector will be, for this charge the position vector will be, it will be nothing. It will be aj cap, and for this charge the position vector will be ai cap, right? And for this charge the position vector will be minus ai cap, and this charge will have position vector minus aj cap, right? So we'll apply this equation. That's net dipole moment p will be for this charge it will be 3q a j cap direction, right? In the j cap direction, right? And for this minus 2q charge it will be minus 2q ai cap, right? Then for minus 2q charge it will be minus 2q minus ai cap, right? And for this q charge it will be plus q minus aj cap, right? So from here the net dipole moment will be the net dipole moment will be 3q aj cap, right? Minus 2q ai cap, right? Plus 2q ai cap, right? So this and this will get cancelled. Minus q a j cap, right? So from here the net dipole moment p will be nothing. It will be 2q a j cap, right? 2q a j cap. So this is the net dipole moment because of these four charges, right? Distributed in this fashion, right? So this will be the net dipole moment, and the net dipole moment, or the direction of the net dipole moment will be along y direction, right? So this will be the net dipole moment, right? That's 2qa, right? This is the net dipole moment, right? This will be the net resultant dipole for this configuration, right? Now moving on to the question number 7, right? The question number 7 says that two spherical conductors of radii 4 meter, right? We have two spherical conductors of radii 4 meter and 5 meter. and they are charged to the same potential if sigma 1 and sigma 2 be the respective values of the surface charge density on the conductors, then the ratio of charge density is, right? Now it's given that the two conductors, right, of radius, two conductors of radius r1, right? One conductor is of radius r1, another conductor is radius r2, right? So both these conductors are having the potential, same potential, that's V and V each, right? Since the radius is different, it means that the charge densities has to be different for these two, right? Now, writing about the potential on this surface, the potential will be nothing. It has to be for any sphere that will be kq upon r. This is the net potential on the surface of a sphere, right? Now, what we can do here is we can write it as q upon 4 pi epsilon naught r, right? If you multiply it by r in the numerator and divide by the r in the denominator, we'll left with the potential that will be qr upon 4 pi r square epsilon naught, right? Now from here you can see q upon 4 pi r square is the surface area of the sphere, right? And charge per unit surface area is surface charge density sigma, right? So sigma r upon epsilon naught will be the equation for the potential in terms of the surface charge density. Now epsilon naught is a constant, right? Here the two spheres have the same potential. It means that sigma will be inversely proportional to the r, right? So the density or the charge density will be inversely proportional to the r, right? Charge density will be inversely proportional to the r, or we can say that the ratio of the two charge densities sigma 1 over sigma 2 will be r2 over r1, right? R2 over r1. Now the value of r2 is 5 and the value of r1 is 4. So the ratio will be 5 ratio 4, right? 5 ratio 4 will be the ratio of the charge densities for the two conductors. Now, talking about the question number 8, right? The question number 8 is the plate separation in parallel plate condenser is T and plate area is A if it is charged to V volt and battery is disconnected, then the work done increasing the plate separation to 2D will be, right? And now we have this capacitor, right? This capacitor and area of this plates of the capacitor is A and the distance between the two plates of the capacitor is D. So the capacitance of this capacitor will be nothing. It will be A epsilon naught over D, right? A epsilon naught over D. Now the energy, let's suppose Q will be the charge of this capacitor, right? Q is the total charge, or we can say the energy stored in this capacitor will be Q square over 2C, right? This will be the amount of energy stored in this capacitor, right? And similarly, now what we do here is that if we increase the distance between the two plates of the capacitor from D to 2D, right? From D to 2D, and the area of the plates of this capacitor remains same, that's A. Now the new capacitance C dash here comes out to be epsilon naught A upon 2D, right? So this is the new capacitance, right? This will be the new capacitance, right? If this is the new capacitance, or we can say this epsilon, the new capacitance will actually become half of the capacitance, right? Previous capacitance, right? Now the final energy stored in this capacitor will be, once again, it has to be q square upon 2c, right? Q square upon 2c, right? Q square upon 2c will be the final capacitance of this capacitor, right? Uh, Now you can see here, in this case, this is the final energy, right? The work done will be nothing. It will be the total final energy stored in the capacitor minus the initial energy stored in the capacitor, right? Now you can see, final it will be C dash here, right? It will be C dash. So the final energy stored in the capacitor, it will be Q square upon 2. C dash is C upon 2. So it will be Q square upon C minus, will be left with the initial energy, that's Q square upon 2C, right? So it will be equal to Q square upon 2C. It means this much of work has been done. This much of work has been done, right? And the value of Q is nothing. It will be equal to CV, right? Value of Q will be equal to CV, right? The value of Q here is CV. So the work done here is nothing. It will be C square V square upon 2C, right? 2C and C will get cancelled. So half CV square will be the work done, right? Half CV square will be the work done, right? Half CV square will be the work done in separating the distance between, or we can say in increasing the plate separation to 2D from D, right? So this will be the work done. Now there is another question, very important question. If the distance between the plates of a capacitor, right? If the distance between the plates of a capacitor of capacitance C1 is halved, and the area of plates is doubled, then what will be the capacitance, right? The question says that if the distance between the plates of a capacitor, right? Uh, if the distance between the plates of a capacitor C1 is out and the area of plates is doubled, right? Then what will be the new capacitance? The capacitance is nothing, it's A epsilon naught over T. Now the new area has been doubled, it will be 2A epsilon naught, and the distance has been halved, right? Distance has been halved, right? It will be equal to 4 times A epsilon naught over D, right? 4 times A epsilon naught over D. So this will be the new capacitance for the capacitor, right? This will be the new capacitance for the capacitor. That's 4A epsilon naught over D. So it means that the new capacitance will become 4 times the initial capacitance, right? The new capacitance will be the 4 times the initial capacitance, right? The question number 10 is that a slab of material of dielectric constant epsilon r, right? A slab of material of dielectric constant epsilon r has the same area as the plates of a parallel plate capacitor, but has a thickness 2t over 3, where d is the separation of the plates. How is the capacitance change when the slab is inserted between the plates, right? Now let's suppose these are the two plates of the capacitor, right? And in these two plates, within these two plates of capacitor, we insert a slab, dielectric slab of thickness t, right? Of dielectric constant epsilon r, right? Of dielectric constant epsilon r. And now, initially, if there is some capacitance A epsilon naught upon D for this capacitor, now the new capacitance will be different from the previous capacitance, right? Because of the insertion of this new dielectric slab here, right? Now you can see here the electric, if there will be some electric field here, that will be sigma upon epsilon naught, right? And the electric field within this slab will be a uniform electric field once again, but the magnitude of this electric field here will be it will be sigma upon epsilon naught upon epsilon r. Well, epsilon r is the dielectric constant for this slab, right? This is the dielectric constant of the slab. Now let's suppose the total potential between the two ends of this capacitor is V, right? It's V. This total potential will be the potential drop across uh, this remaining area, or we can say remaining space here, right? Which is filled with air, right? Of dielectric constant 1, right? So it has to be equal to sigma upon epsilon naught, right? T minus T, if the separation between the two plates is T, right? If the separation between the two plates is T, then the potential drop across these two, across the ends of this dielectric slab will be the electric field, since it's uniform, right? Uniform field, it will be sigma upon epsilon naught into epsilon r multiplied by the thickness T, right? This will be the total potential drop. The capacitance of this capacitor will be nothing. It will be the charge Q upon V, right? Or we can write this V equal to Q upon A epsilon naught, right? A epsilon naught T minus T, right? Plus Q upon A epsilon naught into epsilon R into T, right? Now substituting the value of Q here in this value of V in this equation, so it will be Q upon A epsilon naught, right? Uh, Multiplied by D minus T, right? Plus Q upon A epsilon naught into epsilon R, right? Multiplied with the thickness T, right? Now from here, Q and Q will get cancelled, right? So we'll be left with 1 upon taking A upon epsilon naught as a common, that will be in the numerator, right? So we'll be left with T minus T, right? T minus T plus T upon epsilon R, right? T upon epsilon R, right? So the capacitance of this capacitor will be nothing. It has to be A epsilon naught upon taking T as common, right? Taking T as common, will be left with 1 upon epsilon r minus 1, right? Plus D, right? So this will be the new capacitance of this capacitor, right? New capacitance of this capacitor. Now in this equation, the thickness is given as 2D over 3, right? 2D over 3, right? Now you can substitute the value of thickness here equal to 2D over 3 to get the final value of the capacitance, right? So this is how we can find the capacitance of a capacitor where the dielectric slab has been inserted. Suppose if it has been if T is equal to T, right? If T equal to T, then in that case the capacitance will be epsilon r A epsilon naught, right? Epsilon r A epsilon naught upon D, right? So this will be the total capacitance in this case, or we can say it's a fully filled capacitor with dielectric, right? So if K is the capacitance, then it will be K A epsilon naught upon D, right? So this K is the dielectric constant, right? A epsilon naught upon D will be the net, we can say net capacitance of this capacitor, right? Now, moving on to the question number 11, right? Moving on to the question number 11, right? The question number 11 says that three initially uncharged capacitors are connected in series as shown in the circuit with a battery of EMF 30 volt. With a battery of EMF 30 volt, find out the following, right? Charge flow through the battery, right? Potential energy in 3 microfarad capacitor, right? And the total energy in the capacitor, and fourth is the heat produced, right? Now the total charge flown through this battery is Q, right? That will be nothing. It will be equivalent capacitance of this capacitors multiplied the potential supplied by this potential drop supplied by this battery, or EMF of the battery, right? So their equivalent capacitance will be nothing. 1 upon C equivalent will be nothing. It will be equal to 1 upon 2 plus 1 upon 3 plus 1 upon 6, right? So from here the C equivalent will be equal to 1 microfarad, right? So 1 microfarad will be the C equivalent, or we can say the total charge flow through from the battery will be C equivalent multiplied by V, that will be 1 multiplied by 30, right? It has to be 1 multiplied by 30. So it will be C equivalent multiplied by V, 1 multiplied by 30, right? That is the 1 microfarad, or it will be 30 microcoulombs, right? 30 microcoulombs, right? So this much amount of the this much amount of what we say what we can say that this much amount, or this amount of the charge will be flown through the battery, right? Now, talking about this, if 30 microcoulomb is the total charge flown, right? 30 microcoulomb is the total charge flown, right? Now, talking about the potential energy in the 3 microfarad capacitor, right? It has to be equal to the same amount of charge will flow, or the same amount of charge will be on each of these capacitors, right? That will be 30 microcoulombs, right? 30 microcoulomb will be the amount of charge on each of these capacitors. So the energy in the 3 microfarad capacitor will be Q square over 2C, right? Q square over 2C, right? Now Q square, it's 900 square, right? 900 upon 2C, right? So it has to be 2 multiplied by C, right? 2 multiplied by C, that's 3, right? So it's 900 upon 6, right? So this much of microjoule energy will be stored. Microjoule energy will be stored in this 3 microfarad capacitor, right? This much of potential energy will be stored in this 3 microfarad capacitor. So the total energy stored in these capacitor will be total energy stored in these capacitor. U total will be nothing. It will be half C equivalent V square, right? Half C equivalent V square. That will be half C equivalent is 1, and V square is 30 square, right? That will be equal to 450 microjoules, right? 450 microjoules. So this much of energy will be stored, this much of energy will be stored in all the three capacitors, right? Or in all the three capacitors. And the total heat produced here is, total heat produced here will be the work done by the battery is, work done by the battery is nothing, is the charge supplied by the battery uh, with the EMF V, right? It will be Q multiplied by V. This is the amount of work done by the battery. We can replace Q with CV, right? Or CV square will be the work done by the battery, right? And the amount of energy stored in the capacitors is half CV square, right? It's half CV square, or we can say the heat produced is also equal to half CV square, right? It's half CV square. So the heat produced here has to be equal to half C equivalent V square, right? That will be 900 over 2. That will be 450 microjoules, right? So it means 900 joules of work will be done by the battery. Half of the work then will be stored as the energy in the capacitor, and half of the energy will be liberated or dissipated as heat in the circuit, right? So the heat produced in the circuit will be 450 microjoules, right? So heat produced in the circuit will be 450 microjoules, or we can say the work done by the battery is always CV square, right? This is the CV square is the work done by the battery, right? This is nothing. This is work done by the battery. So the work done by the battery is nothing. It's CV square, right? This is the work done by the battery. Now, moving to the next question, in the given circuit, find out charge on 6 microfarad, right, and 1 microfarad capacitor. So it's actually 6 microfarad, right? 6 microfarad, and 1 microfarad capacitor, right? We have to find out the charge on 6 microfarad and 1 microfarad capacitor, right? You can see here there are three capacitors. Capacitor of my 2 microfarad and 1 microfarad capacitors are actually parallel to each other, right? So their equivalent capacitance will be 3 microfarads, right? And this 3 microfarad capacitor will be in series with the 6 microfarad capacitor, right? 6 microfarad capacitor, that's 3 microfarad and 6 microfarad, right? So their equivalent capacitance will be nothing. It will be it has to be 6 multiplied by 3 upon 9, right? So it will be 2 microfarads, right? 2 microfarads, right? So if we can say that this much of capacitance, this is the equivalent capacitance of this capacitor, right? Or the charge supplied by this battery will be nothing. It will be C equivalent multiplied by V, right? C equivalent multiplied by V. That will be 30 multiplied by 2. So 60 microcoulombs of charge will be supplied by the battery, right? 60 microcoulombs. So if this 60 microcoulomb of charge is supplied by this battery, right? Same amount of charge will be on this capacitor as well, right? There will be some 60 microcoulomb charge will be at this junction. Some of the charge will be supplied to this. Some of the charge will be supplied to this, and the total charge 60 microcoulomb will be supplied to this 6 microfarad capacitor, right? So the total charge on the 6 microfarad capacitor has to be 60 microcoulombs, right? 60 microcoulombs, right? Now talking about this, if this is the charge on this capacitor, right? If this is the charge on this capacitor of capacitance 6 microfarad, right? And then the potential on this will be nothing. The potential on this will be Q upon C, right? Q upon C. So the potential is Q is 60 upon C is 6, right? It has to be 10 volts, right? So the potential on this will be 10 volts, right? The remaining potential will be 20 volts, right? That will be across these two capacitors, right? That will be across these two capacitors. So the potential across 1 microfarad will be 20 volts, right? It will be 20 volts, right? So the charge stored in the 1 microfarad will be Q1, right? Q1 microfarad, that's equal to capacitance of that capacitor multiplied the potential across that, right? That will be 1 multiplied by 20, right? That has to be equal to 20 microcoulombs, right? So 20 microcoulomb will be the charge on 1 microfarad. Then the charge on 2 microfarad capacitor will be nothing. That will be equal to 40 microfarads, right? 40 microfarads. 40 microcoulombs, not farads. So 40 microcoulomb will be the charge on the 2 microfarad capacitor, and 60 microcoulomb will be the charge on 6 microcoulomb capacitor, and 20 microcoulomb will be the charge on 1 microfarad capacitor, right? So this is how we can solve this equivalent circuit, right? Similarly, if you have to calculate the total energy stored in this capacitor, we'll just write total energy as half C equivalent V square, right? V square. Now the C equivalent is 2 microfarad. It will be 1 multiplied by 2, right? V square will be 30 square. That's 900. So it means the total energy will be 900 uh, microjoules, right? 900 microjoules. So this much of energy will be stored, right? If we have to calculate the work done by the battery, so the work done by the battery will be nothing. It will be C equivalent V square, right? Now the C equivalent here is 2. So the total work done by the battery will be V square. That's 30 square, right? 30 square. So the work done by the battery will be 1800 microjoules, right? 1800 microjoules, right? So the heat dissipated here in this case will be nothing. That will be 1800 minus 900. That's 900 microjoules. So whatever amount of the energy be stored in the capacitor, same amount of the energy will be dissipated as a heat, and the sum of heat dissipated plus the energy stored in the capacitors will always be equal to the work done by the battery, right? Work done by the battery. Now let's look at these important questions, right? Very important questions. Now you can see here we have the question: find out the capacitance between A and B if three dielectric slabs of dielectric constants K1, K2, and K3, right? K1 of area A and thickness D1, K2 of area A and thickness D2, and K3 of area A and thickness T3 are inserted between the plates of series plate capacitor of plate area A as shown in the figure. Given distances between the two plates T, right? The two plates is T, right? So the total distance D is equal to D1 plus D2 plus D3, right? I can see here what we have actually, we have divided this capacitor vertically, dividing the distance D into three distances D1, D2, D3. If we divide a capacitor in such a way so that the distance between the two plates of the capacitor change, or we can say if we do not keeping the area same, if we just divide this capacitor by dividing the distance, right, in the form of D1, D2, D3, then the capacitances or the capacitors formed with different dielectric constants, right? Then the capacitors formed with different dielectric constants. Then we can say that all the three capacitor will be in series, right? All the three capacitor will be in series. So the capacitor formed because of K1, K2, and K3, these all the three capacitors will be in series, or we can write all the three capacitors as like this, right? We can write this circuit like this. So this will be C1, this is C2, this is C3. Now we know that C1 will be nothing. It will be the A epsilon naught or K times A epsilon naught upon D, right? So it will be K1, area is A, epsilon naught, right? Epsilon naught upon D. Now the length of this first capacitor, C1 capacitor here, it is D1, right? Similarly, C2 will be here. That will be equal to K2 A epsilon naught upon D2, right? And C3 here will be equal to K3 A epsilon naught upon D3, right? A epsilon naught upon D3, right? Now the equivalent capacitance of this capacitor, because all the three capacitors are in series, that will be 1 upon C1 plus 1 upon C2 plus 1 upon C3, right? So this will be the equivalent capacitance. You just have to substitute the value of C1, C2, and C3 or to calculate the equivalent capacitance across the two ends of the plates, right? Remember one important thing, when we divide a capacitor, right, into two or more than two capacitors, right? If the distance, if they are divided in such a way so that the length between the two plates of the capacitor is divided, keeping the area or keeping the surface area of the plates as constant, right? We're just dividing it like this, in this fashion, right? Keeping the plate area constant, right, for all the capacitors. Then all the capacitor will be actually in series, right? They will be in series, right? They will be the capacitors in series, right? Now let's move on to the next question. In the same way, if we divide this capacitor in such a way, if we divide this capacitor such that we divide the area of the plates, right? If we divide the area of the plates as A1 and A2, right? Then in this case, the two capacitors formed will be parallel to each other, right? The two capacitors will be formed, and the two capacitors formed will be parallel to each other, right? So the two capacitors formed will be parallel to each other. Now let's look at this situation, right? We have the two plates of this capacitor, right? Two plates of this capacitor, right? So this is the total distance between the two capacitors, right? Two plates, that's D, right? This is D, right? I can see here we have divided this capacitor into three different capacitors of different dielectric constants K1, K2, and K3. Now let's see how the division has been done, right? First of all, we have divided the plates of this capacitor into two areas, right? A1 and A2, right? A1 and A2, right? It means that this whole capacitor will be in parallel with this whole capacitor, right? Because the area of the plates have been divided into two, A1 and A2. So this whole capacitor will be in parallel with this whole capacitor, right? In this with this second capacitor, right? But you can see this capacitor has once again divided. This capacitor has once again been divided, keeping the area constant, that's A2, but the distance between these two capacitors has been divided as D1 and D2. It means that K2 and K3, these two capacitors will be in series with each other, right? And these two capacitors will be in series with each other, and these two capacitors together will be in parallel with this capacitor K1, right? Or we can write this equivalent capacitance of this capacitor. These two capacitors will be in series with each other, and they will be together in parallel with this third capacitor. So this will be the equivalent circuit for this. This will be the equivalent circuit for this capacitor, right? Now talking about this capacitor, the equivalent, the value of, let's suppose this is C1, this is C2, this is C3. The value of C1 here will be nothing. It has to be equal to A1, right? Epsilon naught, right? Into K1, right? Upon the length of this length between the two plates of the capacitor, that has to be equal to D, or we can write that equal to uh, yes, that will be D, that will be D, or we can write that equal to D1 plus D2 as well, right? Similarly, C2 will be the capacitance of this capacitor, and C3 is the capacitance of this capacitor, right? So the C2 here will be the area is A2, right? K2 epsilon naught upon the length between the two plates of this capacitor, that's T1, and C3 here will be, it will be K3, right? K3, right? And K3, and the area is once again A2, right? It's epsilon naught upon T2, right? T2, right? Now you can see here, the equivalent capacitance of this capacitor will be nothing. These two C2 and C3 are in series, so their equivalent will be nothing. It will be C2, C3 upon C2 plus C3, right? And the equivalent of these capacitor will be in parallel with the C1, right? So the total equivalent capacitance will be plus C1, right? So this will be the total capacitance or equivalent capacitance of this circuit, right? This is the equivalent capacitance of this circuit, right? So this is how we can find the equivalent capacitance of a capacitor, right? If the distance between the two plates of the capacitor has been divided, or the area of the plates of the capacitor has been divided into two or more than three, more out which capacitor is in series with which capacitor, and which two capacitors or three capacitors are in parallel with each other, right? So this is the way to identify the two capacitors in series and the two capacitors in parallel with each other, right? So we are finished with this electrostatics part 3, right? We are finished with the electrostatics part 3. We'll be stopping here. We'll be discussing rest of the things, or rest of the chapters. We'll be starting with the magnetism, right? Magnetostatics, or magnetic due to moving currents, right? Magnetic due to currents or moving charge. That will be discussed or started from the next session, right? So we'll stop here. Till then, take care and goodbye.